So hello, everyone. My name is Alice Bonino, and I am a PhD student at the University of Birmingham. And today I'm going to talk about eccentricity in coalescing binary black holes in the framework of EffectiveOneBody model and data analysis. And I've done this work in collaboration with many people of the University of Birmingham and University of Vienna in Germany and the University of Turin in Italy. So first of all, I will briefly introduce what EffectiveOneBody Approach is. So as you know, the two-body problem in general relativity is not so easy to solve. Indeed, there are not many analytical solutions to the equations, and the numerical relativity simulations are always very computationally expensive, and the post-Newtonian results are only reliable in the first stages of the spiral, so that not in the strong regime. So that the idea of the EffectiveOneBody approach is, instead of considering a two-body system, to use an effective body that moves in a deformed metric that is deformed by a symmetric mass ratio. So that with the EffectiveOneBody approach, we have an analytical method based on post-Newtonian resummation results that can solve the equation in a faster way, and so that we can have a waveform that we can then use to compare with the signal that we see from the observations. So the first question is, why is eccentricity so important? Why do we care about eccentricity? So as you can see in these plots, eccentricity induces a modulation in the waveform of the signal that we see from the observations. So if we can detect eccentricity, we can really say something about the system that we are studying. In particular, population studies tell us that eccentricity is important to study the formation channel of binary black holes. For example, globular cluster and active galactic nuclei may be good candidate to host eccentric systems. And we can also find effects of eccentricity in extreme mass ratio in spirals, and also when the two-body system is perturbed by a third body. So once that we have the model, that in particular the model I'm studying is the TOB-RSMS model that developed in Vienna and in Turin, is to validate the model. So what do we do when we want to validate the model? We do parameter estimation. So parameter estimation means that we want to infer the parameter from the signal that we see from the detectors. And to do this is not always easy, because our parameter space has a large number of dimensions. So what we use are stochastic methods. And in particular, parameter estimations is studied in the framework of Bayesian analysis. And Bayesian analysis gives us a method to infer the parameters in terms of probability distributions. Bayesian analysis is based on the Bayes theorem, and the key elements of the Bayes theorem are prior distributions that describe the knowledge that we have about the system before performing the observation. Then this knowledge needs to be updated. So when we do the observation, so we need the likelihood, that is the probability of some data given a certain set of parameters and assuming a certain model. And the evidence is the completely marginalized likelihood, that is the probability of certain data assuming a certain model without taking into account the parameters. And using these ingredients, we can find the posterior distributions that we want to see. That is the probability of the parameters that we want to study given a certain data set and assuming a certain model. So now I'm going to show you some results. So I performed some injection studies, and that means that I use a mock signal, so not the real data, so that I knew already which were the parameters I was injecting, and I wanted to see if the recovered parameter were the same. So, for example, you can see here the distribution of the posterior distribution of the eccentricity, and you can see that I recover the parameter I injected, and the same happened for the other injected parameters. And also, I see that there is a correlation between the chirp mass and the spin. That is what we expect. So it seems that the model is working well. And after doing the injection studies, I did an analysis of GW15 and M14. And for example, I changed the prior distribution to see what was changing in the posterior distribution. And as you can see here, the posterior distribution is prior dependent. So for example, for the logarithmic distribution, we have an accumulation near the lower boundary of the prior. So I also performed eccentric analysis on GW15 on M14 and circular analysis. And what I found is that in the eccentric analysis, the results are slightly higher than the one we can find in the catalog from the LIGO analysis. And this is something that we can expect. Indeed, the effect of eccentricity needs to be compensated. And from the circular analysis, for example, this is the value of the chirp mass, and we can see that the value of the chirp mass is closer to the LIGO analysis value. The last step of my analysis, I forgot to say that during this analysis, I used a no-spinning system, and I didn't use noise, and I used the PSD, the LIGO, the design PSDs. So the last step of my work was to calculate, to estimate the eccentricity evolution. And to do this, I use an eccentricity estimator that is reducible to Newtonian mechanics using this formula here. And the idea is to fit the peaks of the frequency to find this function, and then the peaks means the value of the frequency at the aphelion and at the apoastron and at periastron. And then after finding this function, I use this estimator to calculate the evolution. So from what I found from this analysis was that you can see here the dotted line is the injection, and it lies within the 90% interval, and the other line is the median. So we can, it seems also from this that the model and the method is reliable. And from the GW15 on M14 analysis, I found that the system, this is the upper bound of the 90% credible interval. And I found that the system is compatible with a non-eccentric system. And this is nice because this is what we saw in the LIGO analysis. But we can also say that we don't exclude a small value of eccentricity at low frequencies. And
so 2-minute warning. Oh, sorry. That's
in conclusion, yeah, what I've done is that I validate the model, the TOB rest-of-mass eccentric model, and I use the method to estimate eccentricity evolution of the binary system. And then from the GW15 on M14 analysis, I saw that this is consistent with a non-eccentric system. Thank you for your attention.
Thank you very much, Alice. Just see if we've got any questions. So while people are, oh, there's one question here. Greg Ashton says, nice work, Alice. To what extent can we trust the upper bound on eccentricity for 150914, given that your analysis does not include spins?
Oh, I think the upper bound is quite reliable. Of course, I didn't put any evolution for the eccentricity in this case, because this analysis is more delicate. So, for example, I didn't use a spin in this case, so there are other factors that can influence this analysis. But for the upper bound, this is quite reliable. This is also what we found from the LIGO analysis, that the system is not, it doesn't seem eccentric. At least maybe with a more accurate analysis, maybe we could also lower this bound. So.
Okay, thank you very much. Well, I think there's another question here as well. It says, hi, Alice, great talk. Do you plan to use this method for a population of sources?
Sorry, I didn't understand very well.
Sorry, do you plan to use this method for a population of sources?
I didn't do any work with population, but for sure, I think, is it possible to do that? I wasn't planning to do this, but yeah, I think it's possible.